Okay, so in this video, we will consider our sixth problem of optimization, and this is problem number 21 on the problem sheet on optimization. Let's look at the problem. A metal rain gutter is to have 9 centimeter sides and a 9 centimeter horizontal base. The sides making equal angles with the base. How wide should the opening across the top be to maximize carrying capacity? So let's try and visualize our rain gutter. Right, we have the base, the two sides, and it would extend something like this, right? So this is your base, this is the left side and the right side, right? And the rain would actually flow through this gutter. What do we know? Well, the sides are 9 centimeters and the base is also 9 centimeters. So this is 9 centimeters, this is 9 centimeters, and this is also 9, I'll write it here, 9 centimeters. So the length of this segment, and this segment are the same, 9 centimeters each. And now we're asking, and if you think of it, the question, we could have asked it ourselves. How will you position the sides? So at which angle will you position these sides so that your gutter will be able to allow the maximum flow of water, right? So you want to choose the angles for both sides, and we know that they have the same angles. So the opening on the left and on the right is the same. And the obvious question is, well, if you're going to make such a rain gutter, you will try and make it so that you will maximize the possible flow of water, and that's what's called the carrying capacity. Well, the idea is, well, how do you measure the flow of water? If you think of it, this is the area of a cross-section of our gutter, right? If you look at this, you have a trapezoid, and if you maximize the area of this trapezoid, you will maximize the area of the cross-section of the rain gutter, and by the same token, you will maximize carrying capacity, the volume of water that can flow through your gutter per a fixed amount of time. So let's just draw a cross-section of our rain gutter. If you cut through it, what you get is a simple trapezoid. So let's try it here and make it a little larger. Okay, so let's extend this just to visualize. Let's call this angle theta. And you see, by figuring out the choice of angle to maximize the area of the cross-section of the rain gutter, the trapezoid, we will then be able to answer the question of how wide should the opening across the top be. This is this, right? This is the opening across the top. But as soon as we find the right choice of angle to maximize the area of the cross-section of our gutter, we will by the same token have found the length of the opening across the top. Okay. And we're told that the angle, the sides making equal angles with the base. So the angle here is the same as the angle here. And we know that this side equals 9, this side equals 9, and this side equals 9 as well. And now the question is, well, how do we find the area of this trapezoid? The idea is we can break it down into two right triangles and a rectangle. Right? The area of the trapezoid will be the area of this triangle plus the area of this rectangle plus the area of this triangle. But if you notice, these triangles are equal. They have the same hypotenuse, the same length of the base, and because this angle equals this one, then this one equals this one, so they're exactly equal as triangles. So the area of this triangle is the same as this one, and because the opening is the same, the area of this triangle is the same as this one, is the same as this one. Okay, so what is the base of our triangle? Call the base, say, x. If you think of cosine of theta, cosine is the adjacent over the hypotenuse. So cos of theta is x over 9 multiplied by 9, and x is 9 cos of theta. Same for the height of our triangle, call it y. Sine of theta is opposite of our hypotenuse, so sine of theta is y over 9 multiplied by 9, therefore y is 9 sine of theta. And I'll go here with the area of the trapezoid as a function of the angle at the base, theta. And now we're good to go. What's the area of this triangle? It's the base times the height over 2. So it's 9 cos theta times 9 sine theta over 2. But we're adding the area of this triangle twice. So it will simply be the base times the height, gives you the area of this rectangle, which is twice the area of the triangles. So it will be 9 cos theta times 9 sine theta, which is 81 sine theta cos theta. We'll call this function, say, f of theta. It is a function of the angle at the base. So area of the triangle plus this one is the area of this rectangle, which is simply, as we've said before, this times this, 81 sine theta cos theta. But now we're missing the area of the rectangle, but it's the base times the height. The base is 9, the height is sine theta, so we get 9 times 9 sine theta, that's 81 sine of theta. And we want to maximize carrying capacity, therefore maximizing the area of our trapezoid, the cross-section of our gutter, and so we want to maximize our function of theta. If you notice though, we can simplify a little bit. We can factor from both terms an 81 sine of theta. The function ends up being 81 sine of theta times, if you factor this, you're left with cos of theta plus 1. If you prefer, 1 plus cosine of theta. That is the function we want to maximize as a function of the angle at the base. Now if we can, it would be nice if we could have a closed and bounded interval for theta, because sine is continuous, cos is continuous, so this function is continuous. So let's see if we can come up with a closed and bounded interval for the range of theta values. Now think of it. If theta is 0, then your side is horizontal with the base, and you have no area. So clearly, it's not a maximum. And if theta is negative, well, even worse, we still have no area. So theta must be at least 0. And again, we can throw in 0 because it will clearly not be a maximum. If theta is 0, we just have a line which has no area, clearly not a maximum. So we can include 0 in our interval. And how big can theta be? Go up to this vertical side. This is theta being pi over 2, 90 degrees. And what if you had a larger angle than pi over 2? Then the side would be like this and like this. And you'd have a region inside the rectangle, which clearly would have an area less than the area of the rectangle. So once again, clearly, if theta goes beyond pi over 2, you get a region that has smaller area than the rectangle, so clearly cannot give you a maximum. So we can only allow theta to be up to pi over 2. Because at pi over 2, we get the rectangle as our rain gutter. And so for any other larger angle than pi over 2, we have a smaller region inside the rectangle. So the area will be obviously less than the area of the rectangle, therefore it will not possibly give us a maximum. And now we have a closed and bounded interval, and so we're good to go. We know that the maximum and minimum value of the function f on the interval will have to happen to occur at either the left endpoint, the right endpoint, or at some critical point inside the interval. Let's find our critical points by finding the derivative of f. (81) is a constant multiple, so you can leave it up front. We have a product. Sine times 1 plus cos, so we use the product rule. Derivative of sine is cosine, so we get cos of theta times the second function, 1 plus cos of theta, plus, by the product rule, the first function, sine of theta, times the derivative of the second function. Derivative of 1 is 0. Derivative of cosine is negative sine of theta. If you multiply across, you'll get cos of theta plus cos squared of theta negative sine squared of theta. And if you think of it, the derivative is always defined. Sorry. So the only critical points will be values of theta where the derivative is 0. Well, it would be easier if our derivative was a function of only cosine and not also sine. But remember that 1 plus sine squared plus cos squared of theta, right? So if you do Pythagoras' theorem, sine squared of theta plus cosine squared of theta is equal to 1. So you can isolate sine squared as 1 minus cos squared of theta. And so now you'll have your derivative as a function of cosine only. This will be 81. And now let's see. We are negating this, so we'll have negative 1 positive cos squared, but we already have a cos squared, so we'll have cos squared plus cos squared, so 2 cosine squared, plus a cos of theta, and finally negative 1. And this has to be 0. But again, if 81 times something equals 0, well, this must be equal to 0. The question is now, how are we going to solve for theta in this equation? Well, if you think of it, look at this as a function of cosine of theta. You have a cos of theta, and you have a cos of theta squared. So this is a quadratic equation in the variable cosine of theta. So we can use here the quadratic formula. This will be 0 if and only if our variable cosine of theta is negative b, so negative 1, plus or minus the root of b squared, 1 squared is 1, minus 4ac, 4 times 2, 8, times negative 1, negative 8, but it's minus that, so we get 1 plus 8, over 2a, over 2 times 2 over 4, but the root of 9 is 3, so we get negative 1 plus or minus 3 over 4. And let's see, if you take the negative, you'll get negative 1, negative 3, negative 4 over 4 is negative 1. If you take the positive, you'll get negative 1 plus 3 is 2. 2 over 4 is 1/2. So the only way for this to be 0 is if cos of theta is negative 1 or 1/2. And let's see now. If cos of theta, let's look at the first possible value, equals negative 1, well, where is cos of theta negative 1? This is at pi. So theta must be equal to pi. And the other possibility for cosine was 1/2. And if you remember, cosine is 1/2 exactly at pi over 3. That is in radians. If you want in degrees, this is 60 degrees. And now we have found two critical points of our function. At theta equals pi and pi over 3, this equation is 0. But if you go back, our interval for theta was between 0 and pi over 2. Well, pi is outside this interval, pi over 3 is inside, and now we have found our unique critical point inside of our interval. So we now have to look at a table of values, and we are essentially done. Let's recall what the target function was equal to. So our function of theta, the area of the cross-section of our gutter, was equal to 81 sine of theta times 1 plus cosine of theta. And now we will evaluate our function at the key values of theta. Our interval, if you remember, was theta ranging from 0 to pi over 2. So let's find f at the left-hand point of our interval when theta was 0. But sine of 0 is 0, the whole thing is 0, and so the cross-sectional area of our gutter is 0, clearly not a maximum value. Let's look at the right-hand point when theta was pi over 2, which gave us a rectangular rain gutter. Well, sine of pi over 2 is 1, cos of pi over 2 is 0, so this field is 1 times 1, 1 times 81, and so we get simply 81 centimeters squared. And finally, the other point that may give us a maximum or minimum was the critical point theta equals pi over 3. Well, let's see. We have 81 times, if you remember, sine of pi over 3 is root 3 over 2 times cos of pi over 3 is 1/2. 1 plus 1/2 is 3/2. So you get 3 over 2. And this, if you do 3 times 81, 3 times 80 is 240, plus 3 times 1, 3, so it's 243. Divided by 2 times 2, 4, times the root of 3. And then with your calculator, if you compute this, you will find an approximate value of 105.22. And now we have our three possible values for our maximum value. 0, 81, roughly 105.22. This clearly is our maximum possible area. And so the angle theta equals pi over 3 is the global absolute min. Maximum. And so now we have found that if we pick an angle at the base of pi over 3 or 60 degrees, we will have maximized the area of our trapezoid, the cross-sectional area of the gutter, therefore the carrying capacity, and the area is roughly 105.22 centimeters squared. So we can draw our picture. The sides were of length 9 centimeters, so this would be 9 centimeters, 9 centimeters, 9 centimeters, and the way to maximize the area of our trapezoid, the carrying capacity of our gutter, was if the angle at the base was exactly pi over 3, or again, if you prefer in radians, 60 degrees. This is 9 centimeters. This is also 9 centimeters. And this is also 9 centimeters. And the maximum area attained, the cross-sectional area of our gutter, was approximately 105.22 centimeters, of course, squared. But if you go back, just making sure we answer the question was, how wide should the opening across the top be so as to maximize carrying capacity? Well, we have answered the problem, right? If we pick the angle at the base of being pi over 3, 60 degrees, the area is as large as possible, and that's 243 over 4 root 3, approximately 105.22 centimeters squared. But the question was specifically asking for the opening across the top. Well, let's see. If you remember, we had the following picture, right? We had a right triangle here, where the angle was theta. This is 9. This was our x value. This was our y value. And x was 9 cosine of theta. But we reached maximum when theta was pi over 3. Cos of pi over 3 is 1/2. And so we get that x is 9 times 1/2, 9 over 2. And the picture is perfectly symmetric at both ends. So you see that when we choose the angle to be pi over 3 at the base, the area is maximized. That's when x is 9 over 2. So this right here is 9 over 2. By symmetry, you have the same triangle here. This is also 9 over 2. And the length here is 9. So the opening across the top will be 9 over 2 plus 9 plus 9 over 2. Nine over 2 plus itself is 9, plus 9 is 18 centimeters. And now we're just answering the question specifically. We were asking for how wide should the opening across the top be so as to maximize the carrying capacity, therefore the area, the cross-sectional area of the rain gutter. So our answer would be that the area is maximized, therefore the carrying capacity is maximized when the opening across the top is equal to exactly 18 centimeters. And that's it. Now, I'll leave you with one question. I chose to solve this problem by introducing the angle at the base, right? This angle theta. My question to you is, what if we said, could we try to solve the problem without introducing the angle theta? Could we somehow do it? And the answer is yes. And I'll ask you if you want to try and solve the problem using now this approach without using trigonometric functions. I like the use of trigonometric functions here. I find the solution very elegant, but but I'll let you solve the problem again without the use of trigonometric functions, so without introducing the angle theta. So if you go back to the picture, and I'll just set this up, I won't solve it for you, I'll let you complete the solution. This was 9, this was 9, this was 9. And again, we want now to express the area of the trapezoid without the help of the angle at the base and trigonometric functions. Well, you can call the length of this segment x. This we called y, but if we use Pythagoras' theorems, this will be the root of 9 squared minus x squared, so 81 minus x squared. By Pythagoras' theorem, if you prefer, this squared plus this squared is clearly 9 squared, which is 81. And now, well, the area of the two triangles, again, they're the same triangles, these are the same triangles, so the area of this plus the area of this is just the area of the rectangle, which is the base times the height, so x times the root of 81 minus x squared. Plus, of course, the area of the rectangle, base times the height. The base is 9, the height is the square root, so plus 9 times the square root of 81 minus x squared. You can factor the square root from both terms and you're left with an x plus 9 times the square root of 81 minus x squared. So now you have a function of x, not the function of theta, representing the area of the trapezoid. So you want to maximize this function as before. The question is, well, what is the possible range of x values? So your interval. Well, if you think of it, the angle we said was between 0. So if the angle is 0, then x is exactly 9. And if the angle is pi over 2, then x is exactly 0. You have no base. So you see that x ranges between 0 and 9 because we already said that theta was ranging from 0 to pi over 2, which means that x ranges from 0 to 9. So once again, you will have a continuous function of x to maximize over the closed and bounded interval 0 to 9. So you'll tackle the problem the same way, finding the critical points of this function inside the interval, and then evaluating the function at the left-hand point, the right-hand point, and you'll find also a critical point inside of the interval, and you'll get to the exact same final answer, an angle of 60 degrees, but you'll find instead directly the opening of 18 centimeters, because you can see that you'll find a critical point of x equals 9 over 2 for this function over this interval. So try this out. See what the solution looks like if you do not use the angle at the base and trigonometric functions, but instead Pythagoras' theorem and x as your independent variable. So be your own judge. You can decide which solution you prefer. Personally, I like the solution using trigonometric functions. It's a trade-off, right? We trade the square root for a trig function.